So it looks like it found us. Scary, right? And in my defense somewhat, they keep changing it. They like, have you ever been to a website like, I know where everything is, and then they update it, and it's supposed to be better, and you're like, ah. So this is the one where I said history, so we could actually then, you know, go to the history. And it will give you information about what you would expect the, let's see, where did I see that? The trend to be. We could go previous day, things like that. Let me take you out to, I guess maybe the other ones, I'll take you out to IntelliCast. And this is the one where I said, I think Ben Franklin would be pleased. It's almost overwhelming, all the data you can see, but if you simply go to national and surface, surface, current surface analysis, I'm going to go to mixed surface analysis. It will kind of give me at a glance what's going on. It still looks really busy. Anybody know what those blue lines are? They're a type of front. Is it a cold front or a warm front? It's cold front. Cold front. Brr. Okay. So of course we're right here, and things are marching down from the north. If we were to kind of, we could put this in animation mode, we might even see that kind of blue thing move down. What a front means is that actually on this side of the front is cold air, and on this side of the front is warmer air. Like, it doesn't feel warmer to me, right? Well, it kind of means that, relatively speaking, we have warm air compared to what's on that side of the line. What's the red line mean? Warm front, yeah. It's a warm front. Yep. And you would think that warm fronts would maybe come from our south, and they do. So can you see where these semicircles are actually on the north side? That's where the semicircles are showing you where it's going. Just kind of like where the triangles are, they're showing you where it's going. So those are kind of fronts. What's that pink line? The pink line is, I think that's an occluded front. It's alternating circle, semicircle, circle, semicircle. An occluded front is where it's almost like, you know how with a cold front we have cold air, and with a warm front we have warm air. With an occluded front, basically you have cold air and warm air that have kind of converged, and they kind of lifted up, and they've made usually occluded fronts can sometimes bring some nasty weather. Yep, so that's an occluded front. Good question. See this kind of mustache here we have here? What's the L stand for? Low. Yep, L stands for low. Do you see any H's? Oh, H stands for high. Yep, L is low. Specifically, it's low pressure. Kind of like, well, H is a high pressure, you know, like when you go up an airplane, you feel like high pressure. Okay, do you feel like high pressure? Not when you go to a plane, but you feel like low pressure because the atmosphere is getting less. Anyway, what I started to say is, see the kind of, I call it a mustache, where we have that pink occluded front, and then we kind of break it off into a cold front and a warm front. So usually that's a sign of, and it's called an extratropical cyclone. And I know, it's not terrible. But that actually weather, which spans how many states, okay, is a weather system called an extratropical cyclone. Very good. So one last place, I'll take you out to weather.gov. And again, .com will get you .com will get you the Weather Channel, TWC, and .gov will get you here. Okay, the National Weather Service. They're both great, but I feel like the National Weather Service, it's probably a little more solid. I'll show you their forecast map, and when I looked a little bit ago, it was not nearly as busy. So you can kind of see this is their surface map. You see your L's, you see your H's. It's funny because sometimes, you know, I dabble, I'm like, I look here and I look there and I compare the maps. I'm like, well, that's not where they put their L, that's not where they put their H. So this one right now actually kind of shows you some warnings. So the white is the snow warning, the blue is snow and rain, orange is rain and thunderstorms, and green is just rain. So these were where I mentioned as a discussion, so you can actually go and see what they're talking about, what they think is going on up here. As you might imagine, to anticipate the weather, we call that the weather forecast, there's a bunch of computers involved and everything like that to try to kind of say, well, based upon the science of the atmosphere, this is what we think is going to happen. So, yeah. So there's an app for that. There's an app for all this stuff. How many people in here have an app on their phone for weather? Yeah. Not yet?
Well, I have a flip phone, so I don't have.
The flip phone, but on your, do you have it on your computer?
Oh, I don't have it on my computer. No.
Don't have it? Okay, on your computer. But anyway, it's a thought. Okay. So let's take a look at our PowerPoint slides I have to kind of kick us off. Now, currently, this class, meteorology, there's no meteorology class offered, intro to meteorology right now offered on this campus. I think you can take it online, just an intro meteorology class. But so what I started to say is, you know, in the past I've taught this in 16 weeks, and this is kind of distilled down to about 3 weeks. So let's see what we got. Oh, I meant to bring in my props, and I don't want to take the time to get it. I might bring them in on Monday, but usually I have beakers sitting here. So I have beaker with ice, a beaker with liquid water, and then I have a beaker here where I kind of cover it, and my beaker that looks empty actually has water vapor in it. So I'll put it up on the board. So I think we talked about this maybe before: solid, liquid, gas. And this is all water. Cute little water. What's the formula for water?
H2O.
Yep, cute little H2O particles. And here, when water is in its ice cube stage, they're all stuck together. Okay, and I know it's probably can't see it back there. They're all stuck together and they're all connected together. They're all like connected with these what we call intermolecular bonds. Okay, very connected. And so it's basically they just shiver. Okay, they move and then but they don't move much. Okay, low amount of motion. And then if these are my liquid water particles, I'm gonna put a little more space. Well, I shouldn't say space between them. But when I come time to connect them, I'm gonna go ahead and make less connections. Less connections. So I'm going to say less connected, and actually we're going to have to talk about those connections a little bit. Less connected, and I'm going to say more motion compared to solid. And then over here, this is my favorite one. So if I had that beaker that had a cover over it, in this room there's water vapor, and actually that's going to be one of our labs, I think, on Thursday, is to say how much water gas do we have in this room. Starts with our H, we call that actually humidity. What's the humidity in this room? So in this room we have water vapor, and basically there are no connections, and we have lots and lots of motion. That's kind of what we have going on here. So I'll kind of be coming back to that, but in the meantime, so our planet is unique in that we have water in its gas, water in its liquid, and water in its solid state. Gas, liquid, solid. It's unique that way. We looked at the planets. So I think I already told you guys at Venus that Venus might have life in the clouds, but it's awesome. Let's see. What's the word there? Oh, comets. Oh, we talked about comets. Where are comets located? What's that? I heard some say. Okay, yeah, they're comets. Kuiper Belt or Oort cloud comets. Yeah, they come close. They get nudged and they kind of come close to the sun. And they fizz, and that's why we see them in the nighttime sky. You know, and then they come back up here. But yeah, they think that especially early on, most of the water that Earth has and retained came from comet impacts. Anybody know about what fraction of the Earth's surface is covered with water? Half. About 75%. Yeah, 75%. This says 70%, but I've heard 75. About 70% of the Earth's surface is covered with water. I remember it's been a while, but watching that movie, The Water World, I mentioned it here before, The Water World, where there's no land. Okay. Now, what this is showing you, though, this kind of yellow-blue sort of thing, is that, okay, how does that work? Okay, so here's the equator, 0 latitude. Here's the North Pole, and here's the South Pole. Okay. The land is in yellow and the water is in blue. So if this is I'll grab my pen. Is the top part of the thing is the northern hemisphere. The bottom part is the southern hemisphere. Which has more yellow? Which has more land? The north. Yep. So wrong pen. So this is my northern hemisphere. This is my southern hemisphere. This is my equator. Yep. More land. So the northern hemisphere has more land. And these got all the poisonous little critters down here. I don't know. I just think all together. I'm obsessed. So one of the things about water in its solid state, thank goodness, is, I'll even put it up here, is it floats. Water in its solid state floats because it's less dense. Thank goodness for us, because if it sunk like most solids do in their liquid state, most solids will sink in their liquid state, then the icebergs would sink and they would displace the water that they sink into. So the water they sank into would come up. And so anyway. Let's see. Yeah, this one, I doubt if you guys would get. This looks at this beaker right here where I have it covered. Looks like there's nothing in it, but it's mostly nitrogen gas, an 80-20, 80% nitrogen gas, 20% oxygen gas, and some water vapor. And actually, depending upon where you are on the Earth, you're running about 0 to 4% of your gas is going to be water vapor. 0, ooh, goodness, that'd be very, what we call arid, right? 4%, that would be very humid. Okay. And we know that our humidity varies from day to day. I'm going to be talking about humidity. We talk about this in my chemistry and context. Where is the water? Where is Earth's water? And most of Earth's water, you maybe already know this, is salt water. It's tied up in the oceans. Only about 3% is fresh water. And of that fresh water, a large part of it is tied up in glaciers or groundwater. And see that tiny little sliver right there? That is actually the fresh water we have access to. So the fresh water that we have access to, the water in the atmosphere, our streams, okay, our fresh water in general. Now we can pipe it from the groundwater up. We do, but so this slide kind of gets a little bit to over here. Now, when I say motion, you say, no, I'm just kidding. Well, hopefully when I say motion, you say kinetic. Yeah. Something that has a lot of motion has what we call kinetic energy. We talked about this in physics. What's kind of the opposite of kinetic energy? We call it stored energy. So I'm going to repeat. Potential. Yeah, so we have kinetic energy or potential or stored energy. So over here, where I said lots of motion, guess what? It's lots of KE, standing for kinetic energy. Over here, low amount of motion. I'm going to say low amount of KE. And anything in its liquid state, including water, is kind of like Goldilocks, you know, goes in a little bare. Yeah, anyway. Just right. So water will exist in one of these. How many physical phases are there? 3. There are 3 physical phases. Actually, there's a 4th physical phase. A lot of times students, little whippersnappers that y'all are, will say the 4th physical phase is plasma. And I'm like, yeah. And there's something to be said for that, but we're doing 3 physical phases. All matter has blank. So starts with letter M. What did I say over there? All matter has motion. Motion. What did I say? Motion. You say kinetic. So all matter has motion, kinetic energy. And so, let's see, how do I do this temperature? Well, in general, I don't know if this will always work. Well, this will work. Ice cubes. What do you think about their temperature? They're cold. Yep, cold. Low temperature. Okay, and maybe not, you think of this, but gases in general, we're going to say have high temperature. I say that because it feels like I'm contradicting myself, because if I told you my beaker here, and I have, it has water vapor and it's at high temperature, but it's at room temperature.
Yeah, when you were explaining it, you said humidity.
That's true. That's true. Might be connection there. Very good. So low temperature, high temperature, medium temperature? I'll put MOD for moderate temperature. All right. Okay, so solid ice molecules have the blank amount of motion. What do you think? Start letter L, I bet. I'm thinking least. Yep. Okay, and gases have the most amount of motion. Now that's for sure. What about temperature? Okay, let's take a look at this video right quick. This is one where if I'm going to try to put it on loop, but if you blink, you miss it. Let's see, how do we do that? You told me one time. Yep, don't. Well, anyway, I'll just play it a few times. All it's trying to show you is that all matter's in motion, and it's just what we just talked about. Okay, so all matter is in motion, and you're seeing the solid, liquid, and gas. Okay. So over here, what did I say is most connected? Solid or gas? Solid. Yeah. And what did I say about gas with regard to its connections? No connections. Those connections are what we call hydrogen bonds. I'll even put it over here if you've been adding to this. So connections, in this sense, connections between water molecules are equal to what we call hydrogen. What's the symbol for hydrogen? H, yep, hydrogen bonds. Exactly, hydrogen bonds. You got it. So the word there is hydrogen. I put mine. A channel changer. Okay. So electrons are not shared, the word is equally. They're not shared equally. Now, in chemistry, and I'm going to have to erase my, hope you guys all got this because these things are going away. In our chemistry units, we talked about electronegativity. Yeah. And we said with regard to an H2O molecule, here's my H2O. It kind of has this bent shape. Does anybody remember which one's partially negative? Is it the oxygen or the hydrogens? Partially negative. It is the oxygen. It is the oxygen. The oxygen is partially negative, and these are what we call partially positive. That's what we call polarity. That's the polarity of a water molecule. And that's the crux of this connection between water molecules. It is so, once you think about it, you're like, oh, well, that makes sense. So that's one water molecule, and I'm going to saddle another water molecule up, and I'll put it down here. You know, they could have different orientations. So that's my hydrogens, that's my partially negative, partially positive, partially positive. And the way charges work is that the unlike charges are connected to each other. So here we go. All I got to do is find an oxygen of one and connect it to a hydrogen of another. And it's kind of like playing Twister. I could take this oxygen if I wanted to, and I could try to, and I'm not sure it would do this, but I could try to connect that partially negative oxygen to that partially positive hydrogen. I'm not sure, it might swing around or something like that. But those dashes I've drawn are hydrogen bonds. So that is totally good. Partially negative oxygen atom of one molecule can bond firmly with a partially positive hydrogen of another molecule. And I've just used dashed lines instead of the solid line. The solid lines would be what we call the chemical bond, and the dashed line would be what we call the hydrogen bond. So here we go. You can kind of see a little better than I did. Now, how many sides, pick one of these. Let's pick this middle one. How many sides do we have in kind of this shape? I'm liking 6. Look like a hexagon. Hexagon, hexagon, hexagon. Have you looked at a snowflake before or seen pictures under a microscope? No two snowflakes are alike. Okay? And they will have this kind of theme of 6 going on. And that's exactly the crux of why. I'm not saying I totally understand everything about whole ice crystal snowflake thing, but that's where that comes from. Is that not cool or what? So here's the lots of bonding that I talked about over there. Now, so let's see, ice has a lot of hydrogen bond to molecules, while water vapor has no, what would the word be there? No, I think hydrogen bonds, no hydrogen bonds. And that's back to the no connections. Connections and hydrogen bonds are the same thing. So if I have my ice, my liquid, and my gas here, how can I make my ice turn into liquid? Melt it. When we melt it, what are we doing physically to it? For what? Warming it up. Yeah, we're adding heat. So think of this. When you add heat, you are basically breaking some of those hydrogen bonds. That's it. It's exactly what you're doing. You feel the power? Add heat. And so do you see where, kind of like I tried to say over here, you see some connections here, some hydrogen bonds, okay? So that's what your liquid water is. If you were to get rid of no hydrogen bonds, then you'd be at the gas. Which of course we would just heat it up to go from a liquid to gas. Yep, that's it. That's the chemistry. That's what's happening on a... And sometimes, you know, the geek that I am, I just think about that. I just think that is so cool. Okay. So heat, we add heat, and we're all kind of good with that. That heat actually has a special name. We have, I don't know if other heats have special names, but that heat is what we call latent heat. Latent heat. If you're taking heat to break intermolecular bonds like you are to melt on ice, then you are adding what we call latent heat. Let's see, as we heat ice, we are, what do you think the word is going to be? I'm thinking breaking. Breaking some of those hydrogen bonds. We call that melting. So have a figure here from your textbook. It's in the same order, sort of. Well, I don't know. Have a solid ice cube over here. You're heating it up, and you see it melt. Man, you got a lot of liquid water from that. Anyway, so let's look at this little diagram as saying we're adding heat, right? Basically, the first amount of heat, I know it's kind of strange, but, well, first off, what temperature does ice melt at? In the Fahrenheit scale? 32 degrees Fahrenheit. If you take, or if you do the conversion, 32 degrees Fahrenheit is the same thing as 0 degrees Celsius. Yep, 32F. We call that the transition temperature. The temperature at which, and actually it goes both ways. It's the temperature at which ice will melt, and it's also the temperature at which water will freeze, right? It's a kind of a tipping point. So the way this works is, notice that we're starting with an ice cube that is colder than freezing. So this first bit of energy put in is only going to jack the temperature of the ice cube up to its freezing point. Okay, it's going to go from -10 to 0. Then, it's kind of cool, then actually the way we can think of it is it's going to stay at 32 degrees Fahrenheit, 0 degrees Celsius, until it all melts. This little plateau right here is pumping in latent heat. This is the latent heat part. We're breaking chemical bonds. Here at B, actually, now we've melted everything, and now we're going to go ahead and heat it up to, what's the significance of 100 degrees Celsius? Boiling point, yep. It's funny how, you know, we're kind of worried, because if you're like me, you're driving down the road and you have some sort of precipitation event and you're looking at the temperature on your car, your thermometer, you're like, oh no, I hope it's done, you know. So we kind of have the 32, but as it works out, 212 Fahrenheit is equal to 100 degrees Celsius, and that's the temperature at which now you're transitioning from a liquid into a gas. Okay, so hold that thought. So as we heat the water, we can ultimately break all the hydrogen bonds, and the substance, I keep reading my slides, and the substance will become a water vapor. What do we call that phenomenon? There's a couple words for it. It starts with our E or V. What's that? When something goes from liquid to gas. Oh, evaporation. Evaporation or vaporization, same thing. Yep. Yep, that's that transition. Very cool. Again then, well, here we go. This is the other part. Okay, so this segment, let's see, what was the segment? The segment B to C was jacking up the temperature of your liquid, and the segment C to D, you see the plateau again, it's going to hold at basically its boiling point temperature. It's fun to see this happen in the lab. Okay, it holds at its boiling point temperature, in theory, until all of its liquid, all the intermolecular bonds, the connections have been broken, and it's made everything into its gaseous state. At that point, at D then, you've broken all your intermolecular bonds, and you're just jacking up the temperature of your gas. So this would be latent heat of what we call vaporization. This would be latent heat of what we call melting or fusion. Okay, so these are the latent heats. Yep, I just think that's so cool. Okay, something goes from a solid directly to a gas. You're like, are you serious? Dry ice. I don't have any in here, but dry ice is so fun. It's dangerous as heck. Because, I mean, it's really cold. Anybody know play? Yeah, okay. So dry ice, when you get it at high heat, because that's where I get it, is a chunk, but it is a chunk of carbon dioxide. So here's my, and it's usually like this, and the nice lady behind the desk gets it for me, but it's CO2, did I say liquid? It's CO2 solid. That's dry ice. What? Because like in this room, we have it in parts per, parts per billion. I think it's parts per billion CO2. We have some, about 400 probably, 400 parts per billion CO2 with regard to gas, CO2 gas. But in the factories or whatever, they take it and they cool the CO2 gas down, and they pressurize those two things. Cool and pressurize CO2 gas will make it into a solid state. So the thing about CO2, this is dry ice. The thing about it is, if you have it for very long, you're going to see it basically just go away into its gas particles. That's it. So that's what we call sublimation. So again, if you know how to picture CO2, you know how to picture sublimation. I tracked this down a while back, and you know how CO2 is great for making those, like at Halloween, I play with it because I like to make the clouds, you know. And if you watch it right, those clouds kind of sink. I mean, like it might come out of your water and it gets kind of crazy like that. But the deal is I'm like, oh my gosh, I'm seeing, we'll talk about clouds. When you see a cloud, you're actually seeing water in its liquid state, liquid or solid. But I'm like, I'm actually seeing cute little liquid CO2 particles, but you're not. You're actually seeing water that has cooled down. You're actually seeing water, liquid water particles. So anyway, we're going to talk more about that. But sublimation. So it starts with the letter L. The amount of energy needed to cause something to change its phase is called latent heat. Latent heat, sometimes latent energy. It's the same thing. And to me, I can see that. I can see breaking those bonds. So over here, you know, if you've been kind of keeping up with this or whatever, you can go back here. And I usually draw an arrow from left to right, and I would go it this way, and I would say add energy, or I'll call it this way, add latent heat is equal to breaking bonds. When I say bonds, I mean bonds, James Bond. Okay. Well, all right, now this is a little less intuitive. I'm going to go ahead on that same diagram, which is getting very busy right now. I'm going to go down here and I'm going to draw an arrow from the right back to the left again. And if you look at what's going on, it's going from a gas to a liquid and a liquid to a solid. Need to talk about that. But the title of this slide says, and well, I'll get to the title of the slide. I'm going to say, I'm going to say forming bonds, because we are. And if you're forming bonds, you don't have to get out your energy sword and break anything if you're forming bonds. So actually the opposite happens. You could take your wand, put it in front of where bonds are being formed, and your wand would be charged up. I know, magical wand, right? So forming bonds is equal to releasing energy. And I'll go ahead and I'll add to that energy. It's not just any energy. I'm going to say it's releasing, I'll call it latent heat. In parentheses, energy. Oh, are you serious? Releasing energy. Well, when does that ever happen? Let's see. Release. Now, one of the things I'm hoping in this unit to try to kind of make sure we're all on the page about is what we'll talk about. Hopefully on Monday, we'll talk about different types of clouds. But I can't see any distinct cloud. I mean, it's just like, you know they're up there, right? But you can't see the fluffy little distinction there. You have one big layer. A big layer is going to be called a stratus. So actually, we've got a stratus situation out there. Okay, if you have little chunks, that's going to be some sort of cumulus. We have some stratus situation. The other thing is, well, is that stratus cloud, is it low, is it medium, or is it high? So we kind of go 3 general elevations for stratus clouds. I'm thinking kind of middle, so I probably call it an altostratus. I'm going with altostratus. But my point is going to be, anytime we see a cloud, condensation has happened. condensation. So if I were to ask you which one of these is condensation, is it from here to here? I'll call that A. Or is it from here to here? I'll call that B. Which one's condensation? A. Yep, that's it. And heat is released. So, and I don't know how much we'll get into it. The deal that the reason we see clouds, I'll make myself clouded here. And I'll make it a fluffy cloud. This is a type of cumulus cloud instead of stratus cloud. The reason we see clouds is because water is in its, I'll put an L for liquid state. That's one of the things I'm hoping that all of you see. Condensation. We see condensation when you have you're boiling water on the stove, and if you see little wisps of liquid, or not liquid, but you see little wisps of clouds coming off, same deal. Basically, some of that water from your pot in its gaseous stage got into the room and then it condensed. That's it, condensation. And a little bit of energy is released. Okay, so what do we call this transition? When bonds are formed between a liquid to a solid. So letter F, freezing. That's it. Phase change. Bonds are formed and energy is released. So now for those of us who have used ice cube trays in our freezer, kind of think of what happened then is we put that cold water in there, it cooled down to 0 from room temperature, from our faucet temperature, and then as it transitioned from a liquid to a solid, if we could have a little thermometer there just measuring that temperature, it actually released energy, it released thermal energy. I don't know how much it's used, but actually the citrus growers in Florida and such, sometimes they have actually sprinkled liquid water on their plants, knowing that they're going to get a temperature below freezing. And during that transition, it gives a little bit of energy to those cute little leaves associated with the cute little plants to give us our citrus fruit. So we talked about sublimation with dry ice. To me, this one is frost. And we actually call this deposition. So if you think of what frost is, you're like, all right, so I went to bed last night and this is my blade of grass. Here's a blade of grass. I went to bed last night and there was nothing on that blade of grass, right? I got up in the morning and I know that there was water vapor around. And I get up in the morning and now I see the blade of grass and I see specks of ice. We call frost. Now, wait a minute. Okay, so did it go from a gas, so this gas stuff went to a solid. But did it go through its liquid state? No. It went straight from a gas to a solid. We call that deposition. So frost is a good example of that. Okay. So this kind of summarizes what we've been talking about. I think it's a good thing. It says arrows up, energy in. So energy in would be, as I've drawn it up here, energy in is from left to right. Arrows down, energy out. That's from right back to left again. So these are important phenomena that happen in our atmosphere. Well, that's a good place to get to. Let's start with a cheesy song about the hydrological cycle on Monday.